Hello, everyone. So this is a new um, video format I'm bringing. It's 1080p and it's on OneNote on my iPad. I'm just gonna test out a few things. Basically, I wanted to test it out by explaining what Fourier series is quickly, as easily as I can without any or much math. So let's start out by having a graph here. So let's say you have a square wave. Let's make it green. So this is a square wave. It's widely used in electronics, things like this, um, because bits are usually on or off. You can't have them halfway. So you might encounter this quite a bit. A clock also uses a square wave. Anyway, we want to represent the square wave with sinusoids. What's the reason for that? Well, we understand sinusoids really well in math. We can represent a sine wave by having something like this. We can have a cos wave. It's just a phase shifted sine wave. Okay? Now, this square wave we can actually represent with a wave. But how? Well, let's start off and imagine this wave. Let's say it repeats like this forever. So let's say it goes down here, goes down all the way, and it keeps going forever. Okay? So, and imagine that this and this and this and this are all the same, because you kind of want it to stay at the same frequency, or at least be periodic in a way. So now a Fourier series, what it will do is first you try to represent this function. This might be a piecewise function. So let's look at what it has. So here it has 1, or it has, yes, let's say this is 1 and 0 over here, or this is -1, let's say. So -1 and 1. So it has between 0 and, let's say, pi, it has, this is pi, oops, this is pi, let's say. It has 1 at 0 to pi, and then it's -1 at pi to 2 pi, and so on. Now, you can actually have an equation, so a sinusoid, represent it. Now, we're going to have just one sinusoid, being a sine wave, in this case, represented. Now, this is obviously not really good at representing it, right? Because there's a big error margin between here and here, between here and here, and so on. But it does somewhat accurately represent it. If we ignore this whole area, we can actually represent this pretty well. But that's not good enough. So, let's try to represent it a little bit better. So what happens if we add to this another sinusoid? So let's say we add another sine term, but let's say we make it a higher frequency and work it out so the wave looks something like this. So this original wave, we're going to make it look like this. And so on. So now, let's draw it in red. We might have this. It's not the nicest drawing, but you get the point. So there, it might not look like much of an improvement, but it actually is. And you might also notice that this smaller wave over here, so the higher frequency wave, is actually smaller in amplitude. So what we did was have a sine term. Let's say it's sine x. This sine term, this isn't going to be a mathematical thing. It's more conceptual. So I don't want to go into mathematics, but this is sine x, and then the new wave that we want to add to it is going to be sine, let's say 2x. But this wave, we're actually going to make it small. Why? Because if we make it just as large, we're going to get something like this, right? And we don't want that because, first of all, we're actually going to have, so this is actually not the best drawing, but if we actually go through and add, so we're going to have something like go up, then to 0, then up, then to all the way down, and then to 0, and up, all the way down, to 0, up, 0, and so on. And why is this? Because there's going to be destructive and constructive interference when they're both at high. So if they are both high, so let's say they're both at 1. So if that is at 1 and that is at 1, then it's going to turn out to be 2. And this function that we have over here only stops at 1. Now if we have 1 and negative 1, it's going to go to 0. So, and the same thing's going to happen with the negative. So if we actually have negative 1 and 1, it's going to go to 0. And if we have negative 1 and negative 1, it's going to go to negative 2. So we don't want that. We want it to stay at 1. So we actually need to make this one, let's say 1 over 2. So now we can't actually get too far from the value. And let's make this one stay at 1. Okay? So now we're going to add more sinusoids and look at what it looks like somewhat. So we're going to add more sinusoids to this one square. Obviously, again, imagine it goes on forever. But this time, I'm going to have something like this. Now, this is something that looks a lot like a Fourier series, what you would expect from it. So, why is this what it looks like? Well, if we look at the sum, you actually get a bunch of fractions everywhere. So your omega, or your frequency, well, I guess it would be angular frequency, but so 2 pi omega I think is f, but it doesn't matter. Your frequency is going to be very high for the smallest components, and for the lowest component, so let's say sine x is going to have a very low frequency. That's going to have the highest amplitude, I mean. So this is what it looks like somewhat. Now you might notice that this isn't a mistake. I actually drew these things on purpose. This is called Gibbs phenomenon. And that happens when you try to replicate waves. That is just the addition of a bunch of waves. So because you're adding so many waves, so let's say you're adding, let's say 1 sine x plus 1 over 2 sine 2x plus 1 over 4 sine 4x, and so on, let's say. Well, and also, this is probably going to be like this, actually. And then they do switch around. And Fourier series can actually get very annoying with the negatives, because you'll actually have sum of something n to infinity, n equals 0 to infinity or something, and you'll have like n to the, or not n, sorry, you're going to have -1 to the n, and that's going to switch every single time. So when n is 0, this is going to be +1. When n is 1, this is going to be -1, and each time it's even, it's going to be +1. Each time it's odd, when n is odd, the whole thing is going to be negative, and so on. So Fourier series can get very complicated in that respect, but let's ignore the math for now, for a little bit, and look at this. So this is called Gibbs phenomenon. And the reason for this is, again, you get a huge amount of things adding up. And when you have, you can't possibly have infinite sinusoids in real life. So you get these little spikes on the ends. And it looks very weird when you actually see it, but it makes sense. It's the math doing its thing. If you want to get rid of it, well, you just have to add more sinusoids. But it will get thinner as you add more sinusoids, but it will also get larger in amplitude. So depending on what resolution you're using, so let's say this is time, right? So if you use a high enough resolution in time, these spikes might not be seen because they might be, let's say, a picosecond, so 10 to the -12 seconds, and your device might not actually detect that fast of a speed. So if you add enough sinusoids, but also you have to be able to add that many sinusoids to get to that thinness for the Gibbs phenomenon. Okay. Now, next video I plan to do Fourier transform. So I don't want to get into the math because the math is probably the most annoying part of this, and the math gets really tricky, especially if you don't have a background in a lot of basically math, because you don't really need calculus. Oh, I guess you do need calculus because there's integrals in there. So there's calculus, and it's really tedious math, integration by parts and so on. So I'm just going to cover the ideas and the concepts. And yeah, next video is going to be Fourier transforms. That's actually a lot of fun to understand. So thanks for watching, and I'll see you in the next video.